Alright, so today we're going to do the topic 12 stuff, the higher level stuff for topic 2. Um, the only difference here, we reintroduce EMR radiation. The only difference here is that we actually do calculations here. So let's just go straight into the sample question. So a certain energy of violet light has a wavelength 415 nanometers. Calculate the frequency, wave number, and the photon energy of this light. So it's just rearranging equations, plugging and chugging. So here we use C equals the speed of light equals the frequency times the wavelength. Um, we isolate for frequency and so on. And then the wave number is 1 over this. And then we get that. And then lastly for the energy, we just use E equals HF, where H is the constant and F is the frequency, which we obtain from part A. The equations that are relevant here are given in the data booklet, so I wouldn't worry too much. So sample question 2 is, what is the total energy of a mole of photons in the previous question? So we know that for every photon, there is this many joules from the previous question. And then we know that for a mole of photons, that's just 6.022 times 10 to the 23 of them. And then we're just dividing here to get kilojoules instead of joules. And we have 288 kilojoules per mole of electrons. And this is important because this light energy can actually ionize atoms, and the way it does that is photons have a certain energy and they sort of transfer that. And they excite it so much to the point where they excite electrons in the atom so much to the point of just flying off because they have so much energy. The photon gives the electron so much energy it just flies off. So in atomic emission spectrum, there's a convergence of lines between the high energy side of each series. The highest energy instance of convergence occurs at the high energy side of the electron. So basically, remember how in the standard level video we talked about how each light, the energy levels converge to a certain wavelength, like the electronic transitions converge to a single wavelength. Well, that's important because that's sort of the critical wavelength that we need, because that's sort of the critical color, because if we know the frequency of that color, we know the energy difference between energy level 1 and infinity pretty much. So then we know we have to input that much energy, we have to input more than that energy to ionize it fully. So as we can see here, these lines here converge towards this wavelength here. And that means that if we input that amount of energy, it will actually leave the atom. So the energy level transition from 1 to infinity results in ionization of the atom. So in the emission spectrum here, the limit of convergence in the Lyman series is at this wavelength. Calculate the ionization energy of hydrogen. Now, what's important here to note is that this signifies the transition from 1 to infinity, and we know that it absorbs a photon, which has a wavelength of 91.16 nanometers. So first we convert it to meters, and then we use the universal wave equation. So speed equals frequency times wavelength, and then we again use the result here of this frequency to go from E equals HF. So 6.626 times 3 times this frequency here, and then we get that. Since this is just per photon, and we know that we want it in kilojoules per mole of photons, so that's the amount of energy required to ionize one hydrogen atom. What about a mole of them? So then we multiply this by 6.022 times 10 to the 23, and then converting it to kilojoules, we get this number here. Note here that there are some exceptions to the first ionization energy trend that you studied in topic 3. Notice here that there are dips at 13 and 16. And the reason for these dips is that at energy level 13, the p orbital is just has one electron there, and what's important to note is that electron configurations with full sublevels and half full sublevels are actually have a degree of stability associated with them. So therefore, if we just remove that one electron in the case of group 13, it's going to have full orbitals, and therefore that's just a little bit more, that's actually quite stable. So seeing generally as a rule in nature is things tend to stability, it's gonna reward you more or less for doing that by not requiring as much energy. And then similarly for group 16, if we go to group 15, well, here, let's draw this out for you because I think it makes more sense if we draw it. So for for 13, 16, 13, we have S. I'm only drawing the valence band here because that's what we care about. So here we have 1, 2, 3, and then 1, 2, 3, 4, 5, 6. Now, what if now full sublevels are actually stable? So if we remove that, as we can see here, the highest energy level has a full, the highest sublevel is full, and all the other ones are also full. So therefore, there's a degree of stability associated with that. And then similarly, if we remove that one there, that's actually half full, and that's actually somewhat stable because there's no repulsion within that. So therefore, that configuration is slightly more stable than the 16 one. Therefore, it'll reward you by not requiring as much energy. So, um, and also too, what's important to know is that these successive ionization energies prove the structure of the atom. We could actually use it. We can actually use jumps to prove energy levels. So, as we can see here, um, as we can see here, the log of the ionization energy compared to the number of electrons removed. We can see here that it's it's we can see here that there's a sudden jump here, and that jump is corresponding going to the energy level below that, the previous energy level from the valence one. So, and then from that we can also deduce what element it is. So since here we see a jump at ionization energy number 4, that's probably carbon. But what's important to note here is that those jumps that we can see here on this table, there's a little zigzag that indicates these jumps. So here we go from 496 to then all of a sudden we jump to 4500, and then okay, it still increases, but it's somewhat linear. This one only goes up to about 7. This one only goes up by about 2500. That's about 3500, and so on and so forth. And we can see here that there's a huge disparity between here and here. It's more pronounced here if we look at aluminum, for example. Okay, that went up by about 1300. That went up by about 1000, and then bam, it just went up 5 times. And the idea here is that you go to the energy level below that, and that one's full. And we know that um, noble gas electron configurations, which is what the core is, noble gas electron configuration, are really, really, really stable. So therefore, undoing that is not what nature wants, and therefore it's going to resist that as much as possible by requiring an extremely high ionization energy. I think that's everything for today, so thank you. So here, let's actually do number 12. So pause the question now. All right, I think so for all of us here, I think we should start to see which one it is. So straight away, you can see a big gap here in the energy level. We can see a big gap here, here, and here. So there are 3 main energy levels. And if I pull up my periodic table, that should be potassium, because that's in period 3. So that's potassium. And the reason it's potassium is because we have an immediate jump here from the first, so we start with the first ionization energy here. We can see there's a big jump to the second one from 1 to 2. So therefore the second ionization energy is super high, which means that there was 1 valence electron, which means that it was potassium. And yeah, thank you very much.